Hi, Stefan.
Hi, it's nice to see you again, Peter.
Yeah, you too. Welcome to the podcast, Everyday Metallurgy. Today, we're going to talk about a subject that's pretty close to my heart because we're going to talk about metal injection molding. And I have been doing that for 15 plus years now. And what is metal injection molding? Maybe the most famous part, I brought it with me here. It's
Oh yeah.
that guy, the connector piece for the old iPhone, because it doesn't exist any longer.
No.
Uh, so a big change has happened to the global MIM business, and we'll dig a little into that today. But first, will you give an introduction to yourself?
Yeah, that would be great, Peter. Thanks again for having me on the podcast. So my name is Stefan Yerns. I'm the owner and operator of Elnik Systems. I'm actually second generation owner of that business. My father started the company 58 years ago. Elnik is a debind and sinter equipment maker. I'm also the owner operator of DSH Technologies, which is our sister business where we do not just toll debinding and sintering, but we do a lot of technical troubleshooting, process help,
Mm,
and really look at the overall process of, it's one thing to have equipment, it's another thing to know how to make it all and from start to finish, how to make
mm,
the whole process work. And that's where DSH really thrives and
yeah.
shines in the industry. And then I have a couple other businesses I operate. We have a German outfit that
Mm.
is an extension of Elnik as well. And then in 2020, when we all found a little bit more time on our hands to do. I took a hobby of mine of woodworking and I started a little business out of woodworking, and I do that on the
Uh,
side.
yeah. My hobby was to start this podcast.
Everybody found one, right? So
Yeah.
great, and I love the mission you're on with this podcast too, because
Yeah.
I think our industry, like the rest of the world, is changing a little bit, right? There's only so much at trade shows that's still happening, and
Mm,
these podcast platforms, I think, is where people are getting the more open freedom to talk more in depth, about a lot of
mm,
technology and a lot of things that this industry needs. So,
yeah.
I congratulate you on this mission you've set out for yourself. So it's exciting to be here with you.
Yeah. And it's anti TikTok. Because in TikTok you have 7 seconds to catch
Yeah,
and deliver your note. Here you have more than half an hour, so
yeah,
you can really go deep.
yeah. I mean, look at
Um,
everything in the last 5, 6 years, across many different countries, a lot of, even on the political side of the world, a lot of, political candidates that got nominated into some of their roles. Podcasts, I think, were the ability to get to see that person in the truth and the the reality of
mm,
who they are.
yeah.
So podcasts are great. I think it's a little bit of the really how the world is going to share good information going forward.
Mm,
Honest, open, truthful, unedited,
yeah.
just
Exactly.
raw information.
It is. Yeah. But let's jump into MIM, the metal injection molding. For those who are not familiar with it, how would you describe MIM as a technology?
Yeah, MIM is it's a fascinating technology that I feel is under the radar in terms of how many people are aware of its use around the world. But when it comes to, especially us in the field looking at how far it reaches, it's in every technology, it's in every industry. One of the things I love to do as I walk around just general life is look at people's, jewelry and their bags and their glasses. I'm like, ooh, 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 those parts, and kids that are wearing dental braces on their teeth. I'm like, oh, there's another, avenue where the technology really thrives. So metal injection molding it's another forming technology for metal parts, right? So
Mm,
just like machining where you're subtracting material away or welding where you're, fusing material together, metal injection molding takes the plastic injection molding theory and practice and applies it to a metal powder forming technology. So
mm,
in theory, you can't just shoot metal powder into a mold because you open the mold, the powder will fall out. So it's a
mm,
mixture of plastic and wax together with metal powder that gets shaped and formed like a molding practice, like plastic, and
mm,
then needs to go through thermal processing technologies to remove both the wax and then the plastic, and then high enough in temperature to
mm,
fuse that metal together. depending on the type of
Mm.
metal and the temperatures that it needs. So very
Mm.
cool technology. As I said, it's, almost a 50-something-year-old technology now.
Yeah.
But really in the last 30 years, I would say is where it really started to take over. But it applies to
Mm.
every industry, whether
Yeah.
it's the Ray-Bans you put on to feel like a fighter pilot, jet pilot, or a pair of Oakleys you put on, or the braces your kids wear or you wore growing up, or
Mm.
the lawnmowers you ride every day to cut your yard, or the planes you fly in, the cars you
Mm.
drive, the guns you shoot,
Yeah. Yeah.
and it's
Especially
further and further
that.
reaching.
In Europe, the defense industry is growing extremely these days, and MIM is extremely attractive because so many components in that industry are made of metal injection molding.
Hmm.
Uh, because you can get the complexity out of the tool and you can reproduce it with extremely high accuracy. Uh,
Hmm.
so it's a high runner that is exploding these days.
Yeah,
Yeah.
that's a funny
Mm.
use of term there for the defense side. In the United States, also, I'm seeing a lot of money in our industry where people are starting to invest more in technology and
Mm.
not just in equipment, but also in new ways and parts to shape. There's a
Mm.
lot of money coming out of the Department of Defense too. So
Yeah.
I think that's globally right now,
Mm.
especially with the
Yeah.
way the world is at the moment.
Yeah. Typically, I would describe MIM as another way of processing compared to other metal powder technologies.
Mm,
You can make higher complexity. You can make frets
hmm.
in the product. You can make very thin wall. You can do it with a lot of different alloys today, going from stainless, low alloy, soft magnetic, titanium is also coming in,
Hmm.
copper-based alloys. I've even seen tungsten material being mimed.
Oh yeah.
Uh, and I would say a lot of people today, they look into additive manufacturing as the new god of metal powder processing. Uh, but from my perspective, you could reach 90% of the material or the products today being manufactured with additive manufacturing. You could do that with the MIM technology to a lower price with a higher surface finish with a higher reproducibility. Do you agree on that?
Oh, without a doubt. I think the MIM technology, and I've sat in the United States. Currently, I'm representing the Metal Injection Molding Association as the president. I was nominated and voted in for MEMA is what it's called, the organization. But I've sat on the board before. I've sat on other, areas where the industry was used to help market the development boards and so forth. And MIM by itself was this technology that kind of, came out of nowhere once the right equipment hit the world, and then everybody kind of ran with it,
Mm.
didn't want to talk about it, didn't want to share what their secrets were,
Yeah, that's
didn't
right.
do a good job of marketing it, I think, out to the world. Like if you
Mm.
compare metal injection molding as a marketed industry versus metal 3D printing, right?
Mhm.
Almost everybody knows metal 3D printing. They might not know all the nuances, but
Mm.
they know you can 3D print metal.
Yeah.
Where MIM really lost that. And I think some of it was people trying to figure out their technology capabilities and they,
Mm.
wanted to keep it close to their chests.
Yeah.
Yet when you really step back, as an equipment maker of the industry, it's funny to sit there and see everybody be like, "Ooh, we have the secret sauce." And it's like 90% of what you all are doing is the same thing. You know what I mean?
Yeah.
Yeah, there's a couple of little
Yeah.
nuances to
Exactly.
it,
Yeah.
which
Hmm.
makes companies unique and special, but a
Mm.
lot of it's the same stuff that's going on. But you're 100% right. I think in the early days, Metal AM uh, was overhyped, overexcited. We're coming after metal injection molding. We're coming after casting. We're coming after this. It's like,
Yeah.
let's pause and think about it from a perspective. Just like metal injection molding doesn't work in every tool, you don't pull that arrow out unless you need it, right?
Hmm.
Are you a fan of Marvel Comics?
Yes.
Right. So Nighthawk,
Yeah.
the character played by oh my God, I forgot the actor's name, but he shot arrows, right? That was his thing.
Hmm. Yeah.
And his skill set was pulling out the right arrow with the right tip for the
Yeah.
job that he was trying to accomplish. And
Yeah.
that's just the same thing with metal AM versus MIM versus machining versus welding. If
Yeah.
you're making a washer, why in the world would you not either laser cut or stamp it?
Mhm.
You could do it MIM, you could do it 3D printing, but that's
Yeah,
not the right way to do it, right? So I think the
fully
world's starting to
agree.
figure that out a little bit in terms of
Yeah.
capabilities of what 3D printing can do.
Mm.
Um, I don't know about you, but in the last couple of trade shows I've gone to, it seemed a little more boring, which means people are starting to actually apply technology instead of just inventing new ways to print stuff. So,
Yeah, I I think it's right, and I've also seen the AM consolidating a
oh
bit.
yeah.
From going from 100 dreaming companies to a few that are serious and really understand what it is.
Yeah.
But if we jump back in the MIM world,
Yeah.
uh, from my perspective, there are two ways of working. You can go continuous in your process, in your sintering process, or you
Hmm.
can go batch. And some even see it as a religious way of looking at. Oh, no, 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 that's too expensive. If something goes wrong, continuous is so bad. And
Mm,
others say, no, 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 if you go bad, you cannot reproduce. You'll have one way the other day and another product the next day.
mm.
Um, and you are mainly delivering in the batch world. So are you religious about the batch, or do you, or can you objectively tell us a little about the advantage of continuous and disadvantages compared to the batch way?
Yeah, that's a great question. And there are, without a doubt, people I know in the MEM industry that believe only in continuous furnaces, even if they're only pushing 4 tray parts through that thing and then they're done, right?
Yeah.
But it's just what they know, it's what they've grown up with, right? So I think a little bit of it is just what people have grown up in the technology for. But if you step back and take a look at the industry in total, there's 2 areas I want to talk about it. One, if you look at a really good MEM facility, they have a line of batch furnaces that allow them flexibility, material options, alloys that they can play with, and the
Mm,
freedom to control their schedule better. But the right MEM houses also have continuous furnaces too, because they've brought product development and some contracts in house that offer them the ability to push that kind of volume through their facility. So the
mm,
really good MEM houses are kind of a philosophy of both.
yeah.
Continuous furnaces are amazing. Um, they can offer a part cost and throughput then it's really difficult for a batch furnace to ever get to,
Mm,
unless you're looking at like dental brackets, right? That you can
yeah.
do a lot in a batch furnace.
Yes.
But if you're a company that is built on smaller contract or smaller volume size,
Mm,
batch furnaces become more friendly because one of the challenges that continuous furnaces have is they like steady state, right? So if you
mhm,
do a 10 millimeter part in through the continuous furnace and you want to shift over to a 3 millimeter part or potentially bigger, you
mm,
have to regulate and allow that system to kind of get itself back into a
mhm,
new
yeah.
temperature management, adjust
Mm,
the gas flow potential. And where a batch furnace, you don't have to think about that as much. It's just
mm,
build the recipe based on the parts that I'm going to put in. And
yeah.
when it's not running, you can turn it off,
Mm,
right?
yeah.
The other thing that I wanted
If
to
we dig
add
a
to
little
this, because I think
deeper.
it's an important part, right? And we can unpack this a little bit later. But
Mm,
the real big thing between batch and continuous, the way I look at it, when you look at any furnace that's out there, there's 2 furnace types. There's a furnace that pushes gas, and there's a furnace that pulls gas.
mm,
And you can get the push gas in both continuous and batch furnaces. And that's where some of the behavioral and operational differences really start to take foot and take holding. Whereas a pull furnace takes some variables away, but adds costs and equipment costs and so forth. So we can unpack that a little bit later, but that's at least
mm,
how I look at it from a furnace technology perspective.
yeah. I'll dig a little deeper into the technology inside the furnace
Hmm.
because very often a continuous is built with ceramics. And when you run a part at a certain temperature, a certain alloy system, a certain protection gas or active gas, you have an equilibrium with your ceramic or your furnace.
Mm-hmm.
So as you say, if you change temperature, if you change alloy, if you change component size, meaning often component size means that the rest debinding takes place in another actual place in the furnace.
Mm-hmm.
So therefore you remove your equilibrium of your furnace, and therefore you also lose the equilibrium with your ceramics. So it's extremely sensitive, and you cannot just change alloy
Right.
tray after tray. Uh, I agree on that when you say batch furnace are a lot more agile and you can change. But I've also seen in batch furnace with a metal cooled wall, you
Mm.
also have equilibrium.
Oh yeah.
Uh, and I made a trial where I've been centering stainless steel for a long period. There was an equilibrium in the furnace, on the walls, on the heating elements with chromium. Then I changed to titanium and I made titanium black because the chromium compensated on the titanium and created an intermetallic black face.
Yeah.
So it's not that agile as some people say. Are you experienced with that as well? And where are the limits? What can be mixed and what can absolutely not be mixed?
Yeah, that's a great topic. And speaking really into the metallurgy to it, we've all opened the furnace in our lifetime. Anybody who's run a furnace can certainly say they've opened the door one day and be like, what in the world happened? Right?
Yeah.
Continuous furnaces, to close that topic out, the most important thing with them, if you switch alloys or part size, is you have to sacrifice material, even if it's just plain metal. It doesn't have to be
Yeah.
an injection molded part, but
Mm.
sacrificing material through to allow the system to slowly adjust itself into what you're doing. So
Yeah.
you have to plan more with a continuous furnace, any changes. So
Yeah.
you're
We
right. In
use
the
dummy
batch
parts.
furnace, say again?
We use dummy parts for that.
Yeah, dummy parts,
Yeah.
some kind of load resemblance, right, to allow it to change that temperature control.
Yeah.
But those are the struggles with continuous furnaces, where batch
Mm.
furnaces offer you a better, at least out the gate, understanding of how it operates. So
Mm.
the way I look at batch furnaces is a couple different things. Is one, when it comes to managing temperature inside a batch furnace, you have to understand what your furnace technology is capable of. So from Elnik's world, we make furnaces that are anywhere from 20 to 340 liters of process volume. And the medium-sized furnaces and up
Yeah.
have 6 zones of temperature control, because the
Mm.
larger the batch volume, you want more small zones of temperature control, because
Mhm.
it becomes a lot easier to not just transfer the power, but
Yeah.
manage the temperature inside the
Mm.
furnace. So
Yeah.
the
Mm.
most important thing in any furnace is knowing how many zones do I have, how is it being monitored, right? What's the control
Mhm.
thermocouple type?
Yeah.
And on the final side, the analogy I always like to look at is like a guitar, right? Peter, have you ever played guitar in your lifetime?
I tried, but I never succeeded.
Okay, but at least you'll understand this reference, right? So the first time you put the guitar up, if it doesn't sound good, what do? We grab a tuner,
Hmm.
and typically a guitar has 6 strings. Like
Yeah.
a tuner works with it, you strum each individual guitar string and
Mm.
try to tune that guitar to be in a good sounding state.
Yeah.
A furnace requires the same kind of support, right?
Mm.
Especially if you're working with furnaces at high temperature that
Yeah.
have like a type C thermocouple, which out the box has a really big tolerance window,
Mm.
almost 1% at that high
Yeah.
temperature.
Mm.
So knowing what your furnace control thermocouples are, and then doing what we would call like a tuning uniformity survey or systems accuracy test, if you're looking at specifications, to
Mm.
get an understanding of what is the uniformity within my workbox. And if I have zones that are 5, 10 degrees cooler than other ones, does my furnace allow me the ability to offset those zones too, to
Mm.
then find and make a uniform temperature in that box that's more
Yeah.
repeatable and more reliable?
Mm. Yeah.
And then, just like a guitar, right? As you strum that guitar for a month, it starts to not sound as good. You got to go back and tune it again. Furnaces need that same kind of love, right?
Yes.
Thermocouples over time
Hmm.
decalibrate, and
Yeah.
it's really important to know, what
Mm.
that's doing to my parts. So
Yeah.
one, understanding furnace technology if it's doable. But
Yeah.
going into the metal side, that was a really important step of what you said. If you're doing stainless steel every day for 2, 3 weeks, and even above atmospheric pressure, you're still going to drive some of that chromium out, or
Mm.
copper if it's 17.4.
Yeah.
That metal vapor gets everywhere within a furnace, ceramic
Mm.
furnaces, metal furnaces, or even graphite furnaces,
Yeah.
that when you do other metals in there, if they are sensitive, like a titanium, they
Hmm.
will suck that material right into the process
Yeah.
before, it fills the voids and it changes your surface issues. So we have a lot of experience in the titanium world. And
Mm.
what we traditionally recommend customers to do there is, if you're doing a lot of titanium, just dedicate a furnace to that material because it's really important. But if you
Yeah.
want to have the flexibility to move around, before a titanium run, you have to do a burnout run. You have
Mm.
to clean and
Yeah.
burn and bake out all the
Yeah.
impurities that are in that furnace.
Hmm.
And then here's the real secret of titanium that most people don't talk about. In the process area, when I have my titanium, I need sacrificial titanium material.
Yeah.
Have to, whether it's
Yeah.
sponge, powder in a box,
Yeah.
sheet metal, whatever
Mm.
you can get your hands on, you have to
Mm.
put it inside that area because it's going to pick up any further impurities
Yeah.
that
Yeah.
will always come out at some point in
Yeah.
time in the future.
An oxygen getter or everything getter.
You want, if you can be titanium, it's great because it's an everything getter, right? The other
Hmm.
side to it is traditional titanium processing in our industry has always, if you look back in the ages and the archives, it's always done in high vacuum, right? Because we
Hmm.
want no oxygen around the
Yeah.
product. The
Mm.
problem in today's world, when you look at furnace technology, is it's a box in a box with a high vacuum system on the outside.
Mm.
And we're looking at gas flow from a molecular perspective where it's no direct line predictability,
Mm.
right?
Yeah.
It
Yeah.
bounces around in whatever kind of nonsense it wants to do.
Mm.
So
Yeah.
any oxygen molecule in that area still is generally going to find your product or the getter before
Hmm.
it finds the vacuum
Yeah.
exhaust.
Yeah.
So for the last 20 plus years, we've actually been stating to do this in a high purity of argon,
Hmm.
in a low pressure, like 50 millibar, with a lot of flow and argon across the product.
Yeah.
Not only does it keep the surface better from an alpha
Mm.
casing and a cleanliness perspective, but if there's an oxygen molecule in the atmosphere, the argon is thicker and it's just going to pull that oxygen away, and therefore it
Mm.
won't find your part.
Yeah.
And if you bring that argon through a purification
Mm.
system, you've got the absolute top,
Yeah. Yeah, because
atmosphere controller.
you need a high purity argon because
Yeah.
if you take a standard argon 4.0, you might add the amount of oxygen that you remove.
Yeah, and
Mm.
titanium is like the best sponge you can grab under your sink, right? It picks up everything possible. So you
Mm.
got to treat it from a sensitivity perspective. But there's other alloys that are similar. Aluminum is
Mm.
very sensitive. Copper can be sensitive, but it doesn't always play above the vapor temperature of other
Mm.
metals, so it's usually okay.
Yeah.
But those things need to be taken into account, right? Just because you have the flexibility to change between metals in a furnace, you still need to make sure your furnace is operating for you in the way that you need to. And that's where, like a good process coach, like a DSH, like I was talking about earlier, it's
Mm.
one thing to have good equipment, it's another
Mm.
thing knowing how to use it, right?
Yes. Yeah. And I would like to jump back to the tuning of
Yeah.
the guitar because exactly that. Do you need a specific tuning of your guitar if you have another atmosphere, or if you have another setting of your furnitures
Mm.
or parts in the furnace? Because if you have vacuum, you have difficulties in getting the heat in. With the gas can be the heat distributor, but if you have
Hmm.
vacuum, you only have radiation. Uh,
That's a
how
great.
do you do that? Do you make one recipe, one setting per setup of your component or your alloy or your atmosphere type?
That's a great question. And I love that you're really unpacking that more. So there's a bunch of different ways to approach it, right? Let's just say all we're doing in-house is stainless steel and tool steel.
Mm.
You can set one kind of offset into your furnace. But if you're doing really particular metals and alloys and parts specifically, you might want to look at a offset program or management of the controller,
Mm.
particularly to the atmosphere that you're running. And then the real caveat that changes, an empty furnace with just trays and thermocouples versus the same furnace loaded with parts
Yeah.
is going to have a different radiation or radiative
Yeah.
behavior, right?
Mm.
So what we traditionally recommend to do is, depending on furnace capability, right? In our furnaces, we do every atmosphere, all your inert gases, hydrogen and vacuum.
Mm.
And what we'll do is we'll take a nitrogen, vacuum, and hydrogen study of
Mm.
temperature in the furnace all across the same time span, right? Because there's
Mm.
pointless just to heat and cool.
Yeah.
So we go nitrogen, vacuum, and hydrogen. And what I'm looking for is what are my deviations in all three atmospheres?
Mm-hmm.
Because traditionally, your largest deviation is going to be in hydrogen because hydrogen's a great thermal conductor. It steals heat. It likes to run to
Yeah.
cold walls in furnaces and so
Mm-hmm.
forth.
Yeah.
Where in vacuum, you're usually much, much tighter because there's nothing to steal the heat away.
Yeah.
So if I'm going to do a one size fits all kind of approach, I generally recommend customers to do only about 75% of what hydrogen is asking for from a correction perspective.
Mm.
Because traditionally that won't overshoot in vacuum and in nitrogen.
Mm.
But if you want to have one for all three, you just need to, as a user, be religious to go change the offsets if my, if my gas flow or my gas atmosphere changes, or if the furnace company that you're working together with is open to it, you can build in, little dial switches that, depending on my recipe atmosphere, it will
Mm.
either auto switch to a new offset, or I can just adjust it before I go start that furnace run. So
Mm.
everything's a matter of the technology the furnace is capable of doing, but it's really important that
Mm.
knowing that each atmosphere itself behaves differently is
Yeah.
critical.
Mm. Yeah. And this thermal management, when you add parts, sometimes it's very difficult to understand. In a furnace like this, you have on the outside your heating elements where you
Hmm.
have radiation. Then you have an inner wall. So you heat up the wall, and then the wall heats up the chamber. And inside the chamber, you can have one part here, another part here, and a third part here. There'll be
Hmm.
some shadowing. How do you ensure, can you, with your design, your position of the heating elements, the way you build the wall, can you
Mm.
design a better heat distribution so you don't have these shadowing effects during the sintering?
Yeah, that's a great, you're really unpacking technology here. I love this, man. So, I mean, all furnaces are different, right? The right furnace will have some form of a boxed wall, or in our
Mm.
case, what we call a retort,
Mm.
inside their heating element
Yeah.
design. And the
Mm.
reason for that is when you don't have that and it's just an open rack,
Mm.
when you're sending heat from your heater into that area where the parts are, you're going to have hot, cold, hot, cold, hot, cold
Yeah.
spacing across that
Mm.
product, right?
Mm.
So if you have a really thin piece that's maybe a wide dimension, it's going to shrink in areas before other areas come together and shrink. You
Yeah.
want to send uniform heat
Mm.
through a
Yeah.
furnace, right? So when we entered this market back in 1994, the concept of a retort wasn't
Mm.
really available yet on the market.
Okay.
And that's
Mm.
one of the things we brought to the world.
Yeah.
And I did a presentation a couple years ago at one of the MIM conferences here, celebrating one of the guys in the United States named Randall German,
Hmm.
who was kind of well known in the industry.
Yeah.
And I went back and just did some study, and I looked back over the last 25 years and I said, man, when we came to the market, we brought the plastic thermal management and sintering into the same furnace technology and really helped improve time and speed. But the major uniform difference, or the major difference that every other furnace company nowadays is doing, is the retort.
Mm.
So by heating a retort box or a wall, so long as your heat transfer to the wall is good, uniform, and controlled, now
Mm.
you have one big giant heater that is
Yeah.
uniformly transferring heat across your
Mm.
product.
Yeah.
So to your point of shadowing effect, what's critical is, does the furnace operate in a gas flow, right? So the gas can also
Mm.
aid as like a
Yeah.
convection approach towards
Mm.
transferring heat through, as well as the radiation that's moving.
Mm.
If you're in a furnace, and this goes back to the whole push-pull philosophy, if I'm pushing gas into my furnace, the effect of high pressure, low pressure across my product, the way it's staged,
Hmm.
has a big impact on how that thermal radiant heat is also transferred. It
Yeah.
matters more in the debinding phase, but it also impacts the high temperature. Where
Hmm.
if I pull my gas through the furnace, my high low pressure like turbulence that takes place on the backside is
Mm. Yeah.
reduced tremendously. So I'm
Mm.
offering a more uniform transfer of that heat throughout the whole work area. And what's critical is as you're ramping up to your sintering temperature, if you have a really huge heavy mass, you just want to slow it down a little bit to allow that material to slowly transfer heat through it,
Mm.
right? Physics is real every single day. In vacuum
Yeah.
furnaces, unfortunately, we don't go into that deep of a vacuum where we're kind of floating around, but
Mm.
the truth is still there. It takes time to process parts. Can you push a furnace to process, a 5 or 10 millimeter part in 12 or 14 hours? You can, but you might be sacrificing the life of that equipment
Yeah.
and eventually your product down the road. So
Mm.
we're bigger believers in we can find ways to save 2, 3, 4 hours in a cycle time,
Mm.
but don't overdo it, right? You want to get high volume, high yield, great parts out of every furnace, not I pushed it and I turned it over twice and I only got 60% of both runs
Mm.
because I went too far too fast and the material didn't have the ability to properly, maintain itself. So shadowing effect is possible. I would say a good uniform temperature management with a good retort design that allows that heat to be transferred through, and then understanding again how that gas flow inside the oven is making an impact,
Mm.
whether it's being pulled or pushed.
Yeah. And I've also seen some programs where when you're at lower temperatures, before it becomes red, you go with a slow ramp. When
Hmm.
you start seeing it red, you can increase your ramp because the low temperature radiation is not very strong.
Right.
You are dependent on convection. But when
Hmm.
you go higher, radiation takes over, and that
Yeah.
allows you to go higher. Is that also the reason why you see those different slopes of tendering programs?
Absolutely, right? Your point of, once you cross over 800, 900 degrees, you're starting to
Mm.
crawl into that radiation approach in Celsius, and that's where things really start to improve much faster.
Mm.
So, a unique thing about the Elnik furnace is we have a dead center thermocouple in our work zone that kind of simulates what the load is seeing.
Hmm.
And when
Oh,
I look at my traditional temperature graph, right, I
yeah.
hold at, let's say, 400, I ramp to sintering temperature, and then I
Mm.
cool.
Yeah.
That center thermocouple, especially in the low temperature area, it might take an hour or two to get to the 400 degrees where my
Mm.
side control
Yeah.
thermocouples are already at.
Yeah.
And that's a huge impact, right? So
Mm.
everybody says, sintering is the most challenging thing in the world. Honest to God, sintering is pretty freaking easy. It's the debinding that's the most challenging and most
Yeah.
important part because,
Yeah.
especially in stainless steels material, which is the most of the MIM industry,
Mm.
if I leave carbon behind, I run risk of melting my parts and potentially, if it's bad
Yeah.
but ruining my entire furnace.
Yeah.
So
And
debinding is really critical, and without
and you
knowledge of the
don't make
load,
stainless, then you make tool steels.
but the furnace doesn't know that from a recipe perspective, from a
Yeah.
temperature, right?
Hmm. Yeah.
Um, yeah,
Uh,
those are tough moments when you have a customer open up the furnace and things have melted and it's, oh, we wanted to save time. We only ran 60 minutes during the debind. It's like, man, your part's huge. You needed like 4 hours,
mm.
right?
Yeah.
So
Mm.
those are a lot of conversations we have to help people from a process perspective. But
Yeah.
debinding is the most critical part of the process, and there's
Mm.
secrets to it, right? Like
Yeah.
a traditional MIM particle size is 25 microns, right? 20 to 25 microns. If I'm
Hmm.
going and moving into something where I need an incredible surface finish and I go to 10 microns, I just cut in half my particle size.
Yeah.
I cannot use the same recipe that I did at
Hmm.
20
Hmm.
microns,
No.
right? It's like
Yeah.
going to go get an icy, like in the summertime, we all drink like the big icy drinks from 7-Eleven,
Hmm.
right? The Slurpee style drink. The
Yeah.
straw diameter on those things is huge.
Hmm.
If I were to go to grab you a cocktail straw and ask you to drink the drink in the same amount of time, it's not happening. So that's the same philosophy of when you look at getting the binder material away and thinking
Mm.
about porosity, you
Yeah.
got to be mindful of every little variable of the process, the
Mm.
powder, the chemistry of the powder, the type of binder, the particle
Yeah.
size distribution, the parts, the way I'm staging them, the ceramics that I'm
Mm.
using, all of these little variables if I change one, I need to know what that is going to do to the way that the part needs to be processed.
Yeah.
Because if I just assume it's the same, I'm not going to get the same out the back end.
No. Stefan, you're touching upon the most nasty thing in MIM, the debinding.
Mm-hmm.
And doing the debinding in the same furnace as your sintering can be extremely difficult because you don't necessarily know where your condensate ends.
Mm-hmm.
So even when you get it out, they might not go to the trap the cold trap where you want it. What is your philosophy? Are you separating the debinding from the sintering, and how and why do you do that?
Yeah, great question. And again, goes back to every furnace that you have, right? If it's a pull style furnace, you can usually pull that through some kind of trapping mechanism. But if it's a push style furnace,
Mm,
that might just be pushing out an exhaust tube without a trap and it just gets burned at whatever the exhaust burner is. So
yeah.
each furnace makes it a little bit unique in terms of how you have to manage it.
Mm,
When we came into the market back in 94, the technology before the Elnik MIM furnace was first stage binder removal. Traditionally, it was solvent, and then
mhm,
thermal binder removal with pre-sintering in
yeah.
like a kiln or ceramic brick oven, and then a high temperature sintering, either in a metal or graphite furnace, sometimes ceramic too, but depending a little bit on the alloy people were using or availability of technology.
Mm,
That process was almost 3 days to get apart,
yeah.
right? Because a lot of heat up, cool down, heat up, cool down, heat up,
Mhm,
cool down.
yeah.
So the MIM furnace that Klaus, my father, developed together with some people in the industry was there to take the thermal debinding, which was, go to 600 degrees, maybe 800 degrees to pre-sinter and cool, just continue on into the
Mm,
sintering phase. And that shortened the process down to about a day and a half. So we are without a doubt believers in the thermal debind and sinter in the same furnace together. That's kind of the
mm,
bread and butter or flagship system
yeah.
that we have. But to
Mm,
your point, it's the dirty part, right? It's the part that people think they can rush through to get
mm,
to the high temperature, but the rush through is traditionally where furnaces have failures and furnaces lead to, more rapid degradation and deformation. So
mm,
what I always tell people is even for dental brackets, right? It's a tiny little part.
yeah.
Minimum hold at any temperature should be 90 minutes.
Mhm,
And the reason I say this is that you can never over debind your metal parts, but you can
yeah.
definitely under debind them,
Yeah.
right? And if you under debind them, it's when, and the analogy I like to use here is think about a bonfire, right? You just said you came out of the cold winter and so forth, and are fortunately sitting in Copenhagen in a summery day, but you've probably had or will have in the near future an opportunity to sit outside by a bonfire,
Yeah.
right? There's a whole bunch of dry wood we're putting in there. There's friends sitting around, we're joking, we're having a good time. All of a sudden, the dry wood is gone. But I
Mm,
had this wood that's like it sat outside a couple days ago in the rain. I don't know that I want
yeah.
to use it. You have a
Mhm,
choice. I can take that log and throw it right in the fire. Will it dry out and eventually become a piece of wood that will, allow the fire to continue?
mm,
Hopefully, yes.
yeah.
But what happens, right? You create this massive smoke cloud.
Mm.
And usually what happens there is all your friends leave, the party's over, there's no more fire, right?
Yeah.
But if you take the smart approach and you take that log and you set it next to the fire, close enough where it starts to get warm, what
Mm,
happens to that log is you start to see the water vapor
mhm,
driving away,
yeah.
right? And then you turn the log around because it's not heated from both sides, and you do the
Mhm,
same thing on the other side. And once it's done and it starts to get a little char, then you put it in the fire and you're good to go.
yeah.
And that's what I try to use as my analogy for what's happening in the furnace with debinding is we're heating the part up to the right temperature to
Mm,
drive the binder material out in a controlled manner.
mm,
And then when I know I'm done, based on either furnace technology or data to show how long we need to hold, then I can go up to my sintering temperature comfortably and confidently without all the extra carbon. It's the
mm,
extra carbon that causes furnace challenges and furnace issues. But if you give it enough time, or even conservatively a little bit more time, you're going to be sintering with much more confidence and much more reliability and repeatability.
mm, yeah. And you said at the very beginning, when you introduced MIM, you talk about wax and a remaining binder,
Mm-hmm.
a plastic. But there are so many philosophies. There's the wax that can be dissolved in an organic solvent. There's
Mm-hmm.
the PUM that can be removed with nitric acid.
Mm-hmm.
Uh, there are thermal systems. So can you make one furnace that can run on all recipes of binder systems?
Great question. I can make a furnace that can manage all secondary binders, right?
Yeah, yeah.
But when you get involved in MIM, right? So the whole premise of MIM is you have basically a part that's 60% metal powder and the rest is the wax poly
Mm,
mixture, right? And it's that pre-stage wax, whether it's a paraffin wax or polyacetal wax, like the old school BASF catamold material,
mm,
that's where you have to take a nuance and understand, okay, what is this wax and how does it properly break down? And
mm,
then the real reason for those interested in this technology, there's a reason why we use wax for two reasons. One, it's the wax that we make the feedstock warm enough, and it is what carries all the material through into the mold,
mhm.
right? Because
Yeah,
you turn it into like a toothpaste. But
yeah.
then in the first stage debinding a system, if it's like a paraffin wax, you need a solvent debind,
Mhm.
or you can do it thermally.
Yeah.
Or if it's a polyacetal, you need a catalytic debind.
Mm,
Nowadays, there's people playing with that also to be removed thermally, but thermally just takes time. Where
mm,
in a solvent or in a nitric acid environment, or what's coming to the market too is called oxalic acid, these are advanced or more rapid ways to break that material down because it's more of a decomposition than a thermal vapor removal.
mm,
So to the audience, the other reason we want to make that wax be removed first is it creates a porosity channel for the plastic, typically
mm.
polyethylene or polypropylene, to
Yeah.
come out later in its own controlled manner versus forcing its way out of the part later.
Mm. Yeah.
So to make a furnace that can do solvent debinding, catalytic debinding, and thermal debinding and sintering is a little bit more challenging, right? Especially if nitric acid remains a strong user going forward.
Mm,
Nitric acid is very corrosive and challenging in a furnace that also does high temperature work. It would eventually cause a lot of
mm.
degradation.
Yeah.
Oxalic acid is coming to the market. It's something not just our company is in the process of exploring and testing currently as upgrades, but there are some companies and countries around the world that use oxalic acid already. So it's a viable,
Mm.
usable
Okay.
acid. You can buy the
Yeah.
material on Amazon. You can put your hand in
Yeah.
it and
Yeah.
throw it in a box if you want to.
Yeah.
Where nitric
Mm.
acid, if you look at it wrong, it's going to
Yeah.
treat you. It's going to treat you not nice, you know?
Yeah. It's pretty rough. Mm.
Yeah.
Yeah. Uh, if we jump to the centering,
Hmm.
the high temperature level, if we're in steel-based material, we're very often seeing centering temperatures just below solidus.
Hmm.
That means stainless steel has 316, has solidus 1410. So you just have to be below that, where traditional sintering of stainless is done at around 1200. Uh, what does that give, and why do you sinter MIM at these high temperatures? Because temperature costs money, and it costs
Hmm.
material in the furnace.
That's a great question. I'll even add to that, right? So if you look at some of the companies that have come out into the metal 3D printing industry,
Mm,
particularly there's a company called XJet that came out of Israel, right? They used a nanoparticle coated material to jet down into a shape and then
yeah.
printed around that jetted material like a form to kind of hold it in its shape.
Mm,
Very cool technology. The sintering capability of this material is top notch. The surface finish capability was also, really, really amazing.
mm.
Their 316 stainless steel, I could sinter at 1195.
Because the activity level of the small particles is so high.
Right. Where when you
Yeah.
look at metal injection molding at a
Mm,
25 micron average,
yeah.
you need to get to a temperature where you give it enough ability to use the surface area and the energy transfer to fuse.
Mm,
And then the real desire is, and this is where it comes down to loading of binder versus, metal powder and the particle size distribution. If I have too big of a gap,
mm,
right, or interstitial space between the metal particles, Now I need to creep higher and go to the 1400 or the 1405 area where I
Mm.
risk melting, but it's
Yeah.
the only thing I can do to try to fill the void in those gaps.
Mm.
So
Yeah.
a lot of guys in the early binder jet days tried to play with larger particle sizes to make bigger parts, but it
Hmm.
made the sinterability of that material really, really difficult. So
Yeah.
I always take a step back and don't look at it just from the metals world perspective.
Mm.
What I tell customers to do is do what's called dilatometry testing, right? So dilatometry testing, for anybody in the audience who doesn't know, is
Hmm.
basically it's the metal powder sitting in like a little crucible, and there's a probe that's resting on the powder. And as the powder shrinks, densifies at high temperature, the dilation of that probe is showing a curve to
Yeah.
give you an understanding of how the speed and the
Mm.
rapid onset of sintering happens, and then to a point where it hits full dilation, meaning I've hit full density.
Mm.
So that is an incredibly useful tool. And if you don't have it in-house, find a local university or a local laboratory testing
Yeah.
facility.
Mm.
Anytime I make a change, right? Even if it's a different company supplied 316, but the same
Mm.
particle size,
Yeah.
I would recommend to do a dilatometry test because
Hmm.
not only do you see the onset of sintering, but you get to see where the rapid sintering behavior takes place.
Yeah.
And now going back to the conversation earlier about temperature control and temperature uniformity, if I know my furnace can play within 5 to 10 degrees of the temperature I ask it to be at,
Hmm.
now I can really creep towards that solids temperature with confidence and get a density level of 99 point whatever percent in stainless
Mm.
steel, which is not an easy thing to do,
Mm.
right? But
Yeah.
doable if you understand your equipment, you understand the tools
Mm.
you have available to know how this particular material behaves, and then I move my production process forward. And then, just do my PM, do my maintenance, do my testing uniformity on the furnace and
Mm.
keep that moving. This is a viable, repeatable everyday process for you.
Mm. Yeah. And if we look at the furnace materials that can work at these temperatures,
Hmm.
we call them. I think it's a global way of naming it. The furnitures inside
Hmm.
the furnace, the fixtures, the shelves you build up.
Hmm.
Uh, what are they typically made of?
Yeah, that's great. So, I mean, any one of the furnaces used in the MIM world today, you're looking at let's look at it generally from like a cost perspective, right? A
Mm.
ceramic furnace, which means it's lined with ceramic, and then as you get further away from the process area, it gets less dense so that you have better insulation.
Yeah.
That's usually some form of, alumina or zirconia or some form of low grade
Mm.
open frame kind of, ceramic material to provide
Mm.
the insulation. And then your heating elements are usually like moly disilicide, coiled
Oh,
heaters, and things along those lines.
yeah.
The staging mechanisms inside those units can traditionally be metal or ceramic, depends on which one you want to use.
Mm.
But you always need to have ceramic between your metal part and the tray that's carrying it, right? That's a
Yeah.
critical part of the process.
Yeah.
Otherwise, you'll form a
Okay.
beautiful thing called a eutectic, and you're never going to like what it looks like afterwards. So
Yeah. You'll have one
that would be the
piece.
lowest, I'd say, easy entry grade type of furnaces. Then you get involved in graphite furnaces. So you're
Mhm.
looking at traditionally some form of woven insulation pack out of graphite with either foiled or non-foiled edges, graphite or metal heaters like molybdenum heating elements. And then if it has a rack system on the inside, it's usually like an HLM or CFC style graphite racking box inside that
Mm.
unit.
Yeah.
Um, and then same thing, put a piece of ceramic between your part and the tray. And then
Mm.
on the highest end of cost, you're looking at a metal furnace. And the metal furnaces are traditionally made of, forms of molybdenum, lanthanated molybdenum,
Mm.
TZM molybdenum, traditionally for the structure of retorts because it's going to be the best
Mm.
creep resistance and ductile at those temperatures, 12 to
Yeah.
1400.
Mm.
And then heating elements are either molybdenum or tungsten, depending again on the furnace use and the maker of the furnace that's there and the power capability of the unit.
Mm. Yeah. Good description. Um, Now, if we look 5, 10 years ahead,
Mm,
uh, we have to just touch upon it that AM is running fast and has created a name and a lot of attraction. And there are people claiming that AM will take over the MIM business. Do you see that happening, or do you see that AM is just helping MIM to get some attraction from people who have never heard of it before?
Mm. That's a great question, and I think that's a question many people are asking themselves over the last 5 years, right? I think in the onset, everybody said that it will take over MIM, and it will take over casting, and it will take over machining. And
Hmm.
I think if you really step back, I think that theory came from the sheer philosophy of what 3D printing is, and it's the capability to form things freely,
Hmm.
however, whichever way you want. Obviously, some limitations to it, but the ability to freely create on your own, right?
Yeah. Hmm.
Without the need for a mold or a die or a tool or anything along those
Hmm.
lines.
Yeah.
In that concept, I think it has a huge opportunity to take over technology. But when you step back and you ask yourself, okay, let's step back and look at what are all the process requirements along the way. In metal injection molding, if you're dealing with 50 or 100,000 parts per year or more, in many cases, it's very hard to beat that in 3D printing today.
Yeah.
Even in some of the best binder jet systems, which are based on larger volume production, right? Because you don't get the
Hmm.
same surface finish. Some MIM
Yeah.
parts are used right out of the furnace. They don't
Yeah.
need any polishing or cleaning or anything like that. Where
Yeah. They
traditional
are.
AM
Hmm.
parts, they
Hmm.
don't have that same surface finish to it.
Hmm.
So where I think the AM industry will take some of that business away is when people have an honest conversation around, I don't need as much surface finish improvement from what's
Hmm.
here. There's only two areas that I might need a little bit of a cleanup, like a machining step or a polishing step or something like that. But think about MIM, right? When MIM came into the industry, machining was the known way to get complex parts.
Yeah.
And machining had incredible surface finishes, right? As a
Hmm.
as a MIM part maker yourself,
Yeah.
how many times have you looked at a machine's drawing request and said, "Well, I can't produce what you're asking me for,"
Yeah. Exactly. Yeah.
right?
Yeah.
So it shifted.
RA below 0.8.
Yeah.
Hmm. Yeah.
It
It's.
shifted into what MIM became usable for, and
Hmm.
now people started to get a better understanding of what a different surface finish might look like, and then they
Hmm.
accepted it. The same
Yeah.
thing is going to happen with AM too, and AM is going to be, I mean, I've seen it already in my world. A lot of companies are using AM to help companies realize what's possible in metal powder, and
Hmm.
eventually those parts moved into MIM when the production volume increased.
Yeah.
So it is without a doubt the right tool to have. I mean, think about it, right? You have a company that comes in and says, "Hey, I want this part out of metal." If you
Hmm.
could, on Monday get that call, and on Friday when they come to your office, you have a part sitting on the table in
Yeah.
7 variations in front of them,
Hmm.
that's amazing,
Yeah.
right? And that is where it's going to help kind of get some excitement going. But I think we're still, and this is the biggest challenge with 3D printing right now, is I think we're still at a phase where the general understanding of what 3D printing is capable of doing is not as far reaching in the engineering minds, right? Think
Hmm.
about the automotive companies. A lot of people in automotive companies, they don't even know about metal injection molding as
Yeah. That's right.
engineers,
Yeah.
right? So they don't
Yeah.
even know how to think 3D printing yet, and they're
Hmm.
still trying to figure out metal injection molding. So I think
Yeah.
it's a catch up of engineering knowledge and capability,
Hmm.
which through good case studies and examples of 3D printed parts that are successful is
Yeah.
going to make people start to think more about what's potential and what they
Yeah.
can do. So
And,
we're in a
and with
phase
good
of growth it's going to
podcasts.
take. Yeah.
Yeah. Uh, yeah. But I have also seen some requests for where people that came with an AM, but we would like this manufactured with AM, and they were willing to pay a premium. And then we could tell, well, this could be done with traditional existing technology, metal injection molding, but instead of having that RA value 3.2, we can
Mm,
deliver below 1. Is that of interest? Well, is yeah,
yeah.
that's
It's amazing.
it's, yeah, because they had exactly as you described. The marketing level of AM has been fantastic, and the MIM could absolutely learn from that. I don't know if we could take back time 25 years and boost the same level of interest from the MIM. I think the world would look different today.
Agreed. I mean, I don't know where you sit in this thought process, but I do feel that there is some more awareness of MIM coming out to the world because of what AM is saying I can do with metal powder. It's
Mm,
making people ask the question, well, what else can I do with metal powder?
yeah.
So it's giving MIM a little bit of a light,
Mm,
but it's certainly not going to have the
mm,
opportunity that it missed 20 something years ago in terms of just extreme excitement for potential. But
mm.
let's be honest, right? In the early days of metal injection molding, it wasn't as repeatable. It wasn't as consistent. There was a lot of
No.
scrap. People didn't want to
Yeah.
talk about that, right? A lot of
Yeah.
cloning that happens afterwards.
And you could have two alloys, both in stainless, but none of them were not really stainless. so,
Right. Right.
so it was a mess. I agree.
Yeah.
Yeah.
The hype in metal AM came from the fact that in MIM, I don't know that there was as much venture capital money being pushed around to get
No,
this
absolutely
started,
not.
right?
No. It was driven by business request.
Yeah. I mean, I was
Yeah.
13 years old when my dad made the first MIM furnace for Elnik.
Mm,
So I didn't have a worldview of what venture capital money was and all that stuff.
mm,
But uh, the sheer idea of the amount of money poured into 3D printing and the requirement to start to make money back required them to push a technology awareness that wasn't backed by as consistent and as reliable of the equipment that was available because
mm.
shit, I mean, I don't even know how many billions of dollars have been technically wasted in metal 3D printing,
Yeah.
but a lot.
Yeah. That's why it's called a burn rate.
Yeah,
Yeah.
I think that word and terminology came around because of that industry.
Yeah. Uh, Stefan, we've come to an end, and I've only got one question left.
Okay.
You have told a lot about the technology, but if people want to take the even deeper dive, where would you recommend them to go?
Ooh, that's great. Uh, well, I mean, in today's world of AI, you can certainly ask Claude or Chat or whichever tool you want to use to have a good conversation around this technology. But what I would say is first get started with some of the companies that do good publications, right? So there's the powder injection molding magazine that's run out of Europe. There's also manufacturing technology, and then the Metal AM magazine. Those guys do a really good job reviewing what the technology is doing. I would dig into and find as many podcasts like what you're doing here today with Everyday
Mm,
Metallurgy and
yeah.
finding people that are talking about this to learn through some of these good open conversations.
Mm,
And then I would try to figure out ways to attend, whether they're workshops or conferences. Although I have a weird, like, I don't say weird feeling, but I'm getting a sense that trade shows are changing, right? They're not
mhm.
as attended like they used to be 5, 10 years ago, even
Yeah, that's right.
because the ability to do
Mm,
podcasts and Teams calls and everything.
mm,
I would go attend some of these to at least get to know some of the players and the people in the industry
mm.
because the cost of attending an event like that to see that a mass of people is, small compared to making individual trips all over the place.
Yeah.
Um, and then finally, I would say, jump into LinkedIn. I think that there's a pretty good market and network of people in LinkedIn from a
Mm,
professional perspective, trying to do their best to share what the technology of MIM is, the capability, the excitement
mm,
of what it is. And then every country and continent pretty much has a market for it too, right? So in Europe there's
mm.
EPMA that has a MIM organization.
Yeah.
Japan has one of those for the Asian market, and then the United
Mm,
States there's the Metal Injection Molding Association.
yeah.
And then outside of associations there's a group called the MIM Expert Circle in
Mm,
Germany that does a really good
yeah.
job of also
Mm,
reviewing the technology and helping to promote its capability.
yeah. And I would like to chip in. You talked about Ralph German,
Hmm.
and he also wrote a book
Oh
about
yeah.
metal injection molding, and I think that was where I started when I had to learn about MIM, and I think that book is still valuable today to get all the
Oh
fundamental
yeah.
parts of it.
Absolutely. Him together with Animesh Bose, that book is still, I would say, one of the best Bible handbooks you can use. There is another book that a gentleman, funny enough, he was a student underneath Randall German at Penn State. He runs a metal injection molding facility in the United States here called APP, Advanced Powder Products. His name's Don Heaney. He wrote a book also some years ago called The Handbook on Metal Injection Molding. And it's a big, thick book.
Yeah.
And I think what he did a good job there was is he asked people from the industry that had expertise to add to and contribute to what that handbook was for the world. So those two books, I would say, are also great study guides for how to use the technology and how to start applying it.
Fantastic. Let's end on that high note. Thank you very much. I enjoyed our conversation, and I learned something new today. So thank you for sharing.
Awesome. Well, it's been a pleasure. I really, really, meant when I said that I'm a believer in your podcast here. I'm a believer in having this metallurgical conversation out to the world. And I think you're doing a good job of getting, the right candidates and people in front of your audience and to help push this message out there. So thanks for allowing me to be a part of that. It means a lot to me.
Thank you, Steph.